Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to help try and answer the burning question on everyone's mind, what is electric potential? Alright, I'll try to explain this to the best of my ability. We're going to start here. Imagine this, a point charge. And I'm going to say that the charge on this is some amount Q. And just as a quick reminder, what does that mean? Well, this could be maybe a proton or a molecule that's missing a charge, or an electron that's we're a little ways away, or it could be a small object like a cork on a wine bottle or something that's missing a bunch of electrons. Some sort of small object that has extra positive charge in it. And then this Q is going to represent the magnitude of that charge. Now, here's some things about it that we know. If I pick a point in space, like right here, I'm going to call that point P. Right now, there's nothing there. But if we did put a charge there, for example, let's say we put a charge of an amount little q here. If I put that charge there, we know there'd be a repulsive force between these. And that force on this particle would be to the right. The force on this particle would be to the left. I'm only going to draw this one for now. Now, that force is calculated using what's called Coulomb's law, and I wrote this over here, that the force between two charged particles is K, the Coulomb constant, times the first charge times the second, divided by the distance between them squared. There's no deriving this. This is what I would call an observed equation, or a first principle equation. What this equation means is that as this distance gets smaller, this force gets larger, and as this distance gets larger, the force gets smaller. Imagine now that this charge, we let it go, and it accelerates away. And remember that these dots represent like kind of snapshots in time. Now, I'm also throwing an assumption here that this one's staying put. Maybe we've put a nail in it or something, so it's not going anywhere. So this thing's going to leave, and it's going to leave with a certain kinetic energy. Right? When it gets out in this region, it's going to have a kinetic energy equal to 1/2 mv squared. Now, if we plot this force against distance, it would look something like this. We're starting out at a certain value. I'm just going to call that r. In this example, it would be that. This force has a certain value at that location. But the larger r gets, the weaker this force. So we get a curve, it kind of looks, maybe something like this. Ultimately, that force goes to 0. Whoops. Now, here's where the concepts of energy come in. This force does work on this particle. And the work done is equal to this area bound under here. Now, I'm not going to go through, this is not meant to be a mathematical video. I'm going to save the mathematics of this for another video, but suffice to say that is some number, okay? And it's some positive number. So that's going to be some positive number. Now, the electric field creates a force that is a conservative force. It follows the same mathematical conservative laws as a gravitational force or a spring force. And what that means is you can define a potential energy for it. And the potential energy for some force, or let me back up. The change in potential energy is always equal to the opposite of the work done by the field. Now, what that means here, just kind of thinking ahead, is that we have some number which we know is the work term. Oh, sorry about that, my computer's making a value. So what we know is going to happen is there's going to be some sort of drop in potential energy. Now, potential energy can always be measured via some sort of datum. For reasons that I'll talk about later, the datum for problems like this, the potential energy, normally has a datum at an infinite value of r. So we say that when r gets infinitely big, like when this thing leaves, its potential energy is going to 0. Now, backing up, we know now that this system right here has to have a certain potential energy. And here's where the concept of electric potential starts coming in. Whatever that potential energy is, I could have put the proton maybe, actually, I'm going to do this. good enough. Oh, give me a moment here. There we go. That's close enough. There's really kind of a imaginary circle that surrounds this. And I could have put the proton here, 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 here. As long as this distance is same, the potential energy of that proton would have been the same value. So this system carries a property in space with it, and that property is what we call the electric potential. And here's how the electric potential is defined. But EP is defined as potential energy per unit charge. So if I took this system's potential energy and I divided by the charge of this object, I'm going to get some number. Take that potential energy here, divide by the charge, I'm going to get the same number. I can be anywhere on this circle and I'm going to get the same value. And the truth is, it's not really a circle, it's really a sphere. So let me kind of add a third dimension to this. So there is a number that exists that's called the electric potential, and here's how it's defined. It's potential energy per unit charge, so it has units of joules per coulomb. 1 joule per coulomb is called 1 volt. And it describes how much potential energy a given charge would have anywhere on this surface. This surface, this spherical surface, creates what's called an equipotential, because the potential is the same anywhere on the surface. Now, if I imagine a smaller circle, and again, 3D, a smaller sphere, and we kind of think of the effects here, we go back to this graph, we'd be starting at a smaller value of R. So if the proton were released from this point in the circle, we'd have additional work done, which means the potential energy of that proton is higher if it's on this inner surface versus the outer one. Right? What that means in terms of the potential is the potential on this surface is higher than this surface. If we get even smaller, the potential is even higher. So you'll notice that the potential, as we get closer and closer to the charge, is getting bigger and bigger and bigger. And as we get further and further out, the potential is getting smaller and smaller and smaller. Let me talk about how this is relating to electric fields. Right. We also know that these charges create what we call electric fields in the spaces around them. And I'm going to draw in some field lines here. How many field lines you draw is kind of an arbitrary thing. Depends on how detailed you need it, but and again, remember that electric field lines are just lines in space that are basically for visualizing the electric fields. The electric field vectors are always tangent to the field lines. So for example, right here, the electric field would point this way. Right here it would point this way, and so forth. And where the lines are close together, which is closer to the charge, the field is stronger, and where the lines are further apart, the field is weaker. So like notice out here, see how the line spacing is getting larger and larger and larger. So again, let me kind of go back and describe conceptually about electric potential. Here's how that thing is defined. It's potential energy per unit charge. Here's kind of fundamentally what that means. If I pick a point anywhere here, really, let's say right here, and I put a proton here, or any positively charged particle, and I let it fly, so to speak, it's going to accelerate away. There will be some amount of work done by the electric field, which would equal the area under this graph. Now I'm going to save the mathematics of calculating that for another field, or for another video, but for now, suffice to say that is some number. And that work ends up manifesting itself in a kinetic energy term, meaning that this proton will leave with a certain kinetic energy. So the proton's kinetic energy depends on where it starts. If we move inward and let it go, it will leave with more kinetic energy. If we move outward and let it go, it leaves with less kinetic energy. In comes the idea of potential energy. So that proton at this location has a certain potential energy. If I move it inward, it has a higher potential energy. If we move it outward, it has a lower potential energy. And here's where equipotential comes in. Or I'm sorry, electric potential comes in. It is defined as that potential energy per unit charge. So that's a property of space around this charge. It's actually a property of a spherical surface around it. The further out I go from this charge, the lower the electric potential. The further in I go, the higher the electric potential. In fact, the rule that I always make students memorize. Anytime you move with the electric field, you're moving towards lower potential. If you move against the electric field, you're moving towards higher potential. And if you move perpendicular to the electric field, you're not changing in potential. So electric potential is potential energy per unit charge. It has to do with basically the amount of work that the electric field can do on a system as a charge moves away from it. So anyway, that's my attempt number one here to conceptually describe what electric potential is. I hope that this has helped with that. Have a great day.